Yes, it's time now. I shall start this session. Hi everyone, welcome to the third weekly live session of the course Remote Sensing Principles and Applications. This course has been taken by NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research in IISc Bangalore. And this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. Uh, Before starting the contents, I would like to give a brief about the information regarding it. So, I have been recording all the videos of these live sessions on the YouTube channel, which I have already shared with you. The files relevant to the live sessions, I mean the video lectured as lectures uh, as well as the PDF slides will be made available immediately after the class in a Google Drive folder. And if I am using some images from the internet, they are solely for the purpose of education. So as you can see, this is the NPTEL. I mean the channel, YouTube channel, in which I am actually uploading these videos. You can go to this Google spreadsheet and you can find the links for the YouTube videos as well as the uh, Google Drive PDF documents, which has the illustrations of all the solved examples as well as the discussions which we have conducted over the two earlier conducted weekly live sessions. So let's start with the questions. So currently we are at a stage of we are starting with the application part of remote sensing. From this week onward, the emphasis would be more on the application part of remote sensing itself, and I believe it would make the course much more interesting because probably many people might have opted for this course because of this sole reason, because it is highly application oriented. So let's see. So the first question is about the method of movements is used to determine. uh, uh, you know it already from the class. The short answer would be spectral characteristics, but I would be giving a detailed overview on it. Okay, so the answer is basically spectral characteristics, but I will be giving a detailed version also. Okay, so let's see. Let us suppose this is any terrain. Let this be a water body. Let there be grass or any kind of vegetated surface on the floodplains. Okay, so let us suppose a radiation actually energy, strikes the surface. We call it as EI lambda, which is nothing but the incident energy. Some part of the energy will be reflected back into the atmosphere, which we are terming as ER lambda. I will be giving the notations, explaining the notations a bit later from now. A part of it will get absorbed into the water body, let us say, that is EA lambda, and a part will be transmitted, that would be ET lambda. So EI lambda is the incident energy which falls on the surface. ER lambda is the reflected energy. EA lambda is the absorbed energy by the surface, and ET lambda is the transmitted energy. So let us suppose we are writing an energy balance for this case. So what would it be? The initial incident energy was EI lambda, and it can be fragmented into its different components. The components would be ER lambda plus ET, T lambda plus E A lambda. Why am I using lambda is because these features will depend on the wavelength, incident wavelength of light a lot, and that is why I'm using lambda specifically. So what if I want to find out the ER lambda, the reflected energy fraction? So that would be EI lambda minus the summation of the absorbed energy and the transmitted energy. Let me take another slide. So this reflected energy, which we observe as the reflectance, which is basically nothing but the ratio of the reflected energy to the incident energy, will depend on the Earth surface features. And it will also vary at different wavelengths. And that is why I've used lambda with each of the notations. Even if they are just the same, even for the same surface type. Let us suppose the surface is, let us say, concrete. Then uh, a heterogeneous concrete, let us say, it cannot guarantee that the ER lambda to the EI lambda fraction, which we technically call as a reflectance, will be the same always. It changes with respect to the wavelengths. It also changes with respect to the little heterogeneities on the surface, and of course on the illumination also. The illumination being vertical versus oblique, they change the reflectance too. So let's take the first such example to understand how the reflectance changes for different surface features. Uh, yes, so reflectance would be E R lambda, and reflectance will also be a function of lambda. So uh, it can be represented as REF lambda by EI lambda. So one thing is for sure, that this reflectance can never exceed 1 or 100 percentage of the incident energy. That is for sure, and it can of course not be lesser than 0 also. So let's take the first such example, a very famous example by the way. So on the x-axis, it's the wavelength. Let it be in micrometers. And on the y-axis, it's the reflectance. Suppose it is in percentage. So we are just normalizing it from 0 to 1 to 0 to 100. That's what percentage is. That's what percentage actually does to any normalization. I mean that is how percentages actually convert. Any number between 0 to 100. Okay, so for the two types of fundamental forested types, the reflectance values would refer like this. So this is, let us suppose, 0.4 micron. This is, let us suppose, 0.5 micron. This is 0.6. This is 0.7 micron. And this would be around 0.8 micron. This would be 0.9 micron. So first of all, the graph is not made on scale, so please don't look at that for the time being. The solid line would represent deciduous forest, deciduous trees like maple. Deciduous trees are the ones which shed their leaves using under adverse conditions, maybe when they face lack of energy or when lack of water. So Indian deciduous forest, mostly in the peninsular part of India or in the central part of India, they shed their leaves usually during the summer seasons. But in Canada or the higher latitude countries, they usually shed their leaves during the typical autumn seasons. Okay, so that's the basic difference. And the dotted line curve, I mean, is for coniferous tree like say pine. Okay, so we do see that the reflectance changes between the two different tree types also for pine versus maple. And another interesting thing which we see is that the reflectance features are pretty similar in the visible range. Zero point 0.4 visible range, as we all know, lies from zero point 0.4 micron to zero point 0.7 micron. We all know that. And zero point 0.4 to 0.4 to zero point 0.5 is primarily the blue band, roughly speaking. Zero point 0.5 to zero point 0.6 is roughly speaking the green band, and zero point 0.6 to zero point 0.7 is roughly speaking the red band. Okay, so we do see that, I mean, so this is the visible range. Zero point 0.4 to zero point 0.7 is a visible range, that is the one which we human beings can perceive from our naked eyes. Okay, so this is the visible range. We also see that the highest reflectance in the visible range is observed in the green band feature, and that is why we see the leaves or the trees to be green in color. Now there is even a much higher reflectance as we move from the visible range of wavelength to a near infrared range of wavelength. And we actually do see that the maxima of the reflectance curve with respect to wavelength actually appears in the infrared electromagnetic radiation spectrum. So just to sum it up, from these two plots we can infer that the spectral reflectance curves are almost similar in the visible range. But it varies in near infrared range. So we can actually distinguish, I mean, if you are if you are observing the top of the canopy of, let us say, a deciduous tree versus a coniferous tree from a satellite image, you will be able to distinguish these two images, although they will look green to, I mean, both the images will look green from the top, but you will be able to distinguish them. How I am telling you? So suppose you are getting, I mean, the reflectance of a canopy, the top of the canopy of top of canopy. I mean, you are observing the top of canopy from a satellite remote sensing based sensor. So the reflectance in the visible range for both the pixels may be very similar actually, because you don't see a lot of difference in the reflectance patterns in the visible range. They will all look green, predominantly green. But when we have a band which falls in the near infrared region, we will see that the reflectance for the deciduous tree is much more than that of a coniferous tree like pine. So that is how we can actually segregate or distinguish the two different type of vegetation feature. Okay, another thing, another very interesting example is about how to distinguish artificial turf, which is basically artificial laden grass. It's not even a living organism, versus that of a grass. Okay, let's see. We can distinguish that also using spectral reflectance curves. So this is, let us say, the reflectance, and this, let us say, is the wavelength in micrometer. So this is the uh, I mean, we transition from the visible spectrum to that of a not near infrared spectrum. So the dotted line are the dotted line indicates the spectral reflectance curve for the artificial turf, whereas the solid line is the one for natural grass. They both would look very similar. I mean, if you I mean, observe it under a visible spectrum range, that is what we do. I mean, using our eyes also. I mean, by our eyes, I mean, if you are observing something, I mean, an astroturf, which is artificial turf, versus that of a natural grassland, the colors would look pretty similar. But how to distinguish that? You distinguish that using the near infrared band. So this is zero point 0.5, let us suppose is 0.4, 0.5, 0.6 micrometers, 0.7, and this can be as large as 0.8 and 0.9, the near infrared zone. The reflectance can be at as much as 50 percentage, in fact, and for artificial grass it will be even less than 20 odd percentage. And for the previous case, the maximum reflectance can be as much as 40%. Of course, it depends on several other factors also. How much water is available in the leaf of the tree, how much stressed is the vegetation, and everything. So, we will be discussing it in due course of time. The coniferous reflectance can be around 30%, a bit less than 30%, in fact. Okay, another very important application, as it is a civil engineering based course, so the three most prominent surfaces which we feature as civil engineers are number one, vegetation; number two, water; and number three, soil. So let's see, are there spectral reflectance? I mean, differences between these three features, surface features? If there are, then how can we find them out? Let's see. So this is again the spectral reflectance curve. Reflectance, and this is the wavelength. Lambda in micrometers. This is that of water. This is that of. Sorry, someone is trying to enter the. This is that of a healthy green vegetation. So after a relatively small reflectance in the visible region, the reflectance curve will peak at the near infrared region. Then there will be some valleys also. I will explain why they do happen. Okay, and finally there is one such reflectance curve for the clear water also. Okay, so this is dry bare soil. This is green healthy green vegetation. and this is clear water. The reflectance here may be 10 percentage, here it may be around 20. It will vary. It is basically an average spectral reflectance curve, so it will vary definitely. Here it may be 40%. Then this graph is not made on scale, so yeah, beware of that. Okay, so the three common features, I mean, the surface features which we mostly encounter are vegetation versus soil versus water as civil engineers. Let's see what the differences are in terms of spectral reflectance properties. The first one is vegetation. Vegetation, which in this case is healthy and green. So as you can see that this healthy green vegetation actually shows a peak and a valley kind of a response. So we call it popularly as peak and valley configuration. So there are some dips here. The first dip happens here, second dip, then again a third dip. So there are certain dips also. So this dip may be around 1.9 micrometers. The first dip is around 1.4 micrometers. And this is the visible range around 0.6, the peak, which is the green color, and that is why you see the vegetation to be green in color. Zero point 0.4, the end happens around, let us say, 0.8 in the near infrared region, and so on and so forth. Okay, so anyways, so its properties, as you can see, that this healthy green vegetation curve actually shows very distinguishing properties across the visible range, in the near infrared range, and the beyond near infrared range. Someone is trying to enter, I believe. No. Okay. Hello, Mr. Gurumurthy. Can you mute yourself? Or do you want to ask something? Okay, I will do the same. But if there is anything to ask, please feel free to interrupt me in between and ask the question straight away. So in the, I mean, we will use another slide to discuss this, by the way. So the first one is the visible range, which we know is from the zero point 0.4 micron to 0.7 micron range. It is primarily visible range. It is primarily controlled by chlorophyll. We know that chlorophyll is the reason why the leaves appear to be green in color to us. We know that very well. Chlorophylls are also the, I mean, the pigments, the chlorophyll, they are the reason why photosynthesis actually happens. We know that already from our basic science classes. So these chlorophyll pigments, they strongly absorb energy in 0.45 to 0.65 micrometer range, which we technically call as the chlorophyll absorption band. Now, what happens if vegetation is under stress? Then that would mean that the chlorophyll content would be less. That is why a stressed vegetation looks a bit yellowish or reddish in color rather than being green. So that would result in the red reflectance to be increasing. Why? Because the chlorophyll absorption band primarily happens in the red band itself. If the absorption decreases, the reflection proportion has to increase, and that is why the red reflection increases, and that is why a stressed vegetation usually looks to be red in color. So this was a storyline about the visible range. Let's see the storyline for the near infrared range. Near infrared range. Near infrared range we call from 0.7 micron to 1.3 micron. So in this range we observe that the vegetation show very high reflectance, usually in excess of 50 percentage. That's what we see here actually. The reflectances are massive actually in the near infrared zone. And the remaining energy, that is incident energy minus the reflected energy, so that remaining energy usually gets transmitted. Absorptance is very low in this near infrared range, by the way. So how do we get whether a vegetation is stressed or not, healthy or not? That we usually do by understanding the spectral reflectance features in the near infrared zone. So this is, let us suppose, the reflectance in percentage. This is the wavelength in micrometer. So these are the spectral radiation reflectance features. Okay, so we know this curve already. I mean, I've already explained it to you a lot of times. So this would be the near infrared zone. This would be the near infrared zone. So the one which is showing higher reflectance would be the healthy vegetation, whereas the one which is showing a lesser reflectance is the stressed vegetation. So this near infrared range is primarily useful for stress monitoring, species identification, as I showed between the deciduous and conifer forest, or health monitoring. Now coming to the third distinct wavelength pattern, which happens beyond 1.3 micrometer range. So beyond this, this again shows some typical kind of dips in between the vegetation curve. By the way, what might be the reason behind it? Let's see. So it mostly reflects or absorbs radiation with little transmittance. And you also see that there are some dips at some particular wavelengths. So this is the first one, this is the second one, and there would be another one which I have not shown here. So at 1.4 micron is the first dip, at 1.9 micron would be the second dip, and at 2.7 micron, water in leaf absorbs the radiation strongly which we call as the water, technically as water absorption bands, similar to chlorophyll bands. Now, usually the leaf reflectance is inversely proportional to the amount of water in the leaf. So, more the water, lesser would be the reflectance, and vice versa, in general cases, of course. So, we discussed everything about the vegetation, a healthy green vegetation for the time being. Let's move to the second major land class, that is of dry bare soil. Dry, bare, brownish, brown colored, and loamy soil. So in soils, the soil reflectance is actually extremely complex, and it is governed by an interplay of multiple factors. So soil reflectance will be affected by several factors. One of them is moisture content. Second one may be soil texture. Texture means how much amount of the soil is clay, or how much is sand, or how much is silt, or surface roughness. Usually, increase in the surface roughness decreases the reflectance, or the amount of iron oxide in the soil. Usually, that also decreases the reflectance. So, in a way, you can empirically find out the iron content in soil also just by looking at the satellite image. There are certain cautions to be taken for it, of course, but yeah, this may be one way to find it out. Or organic matter content. Organic matter content, in generally, increase in the organic matter content would result in a decrease in reflectance. So we discussed about the vegetation, healthy green vegetation, and the dry, bare, brown, loamy soil. So the third surface feature would be clear water. So in this case, you see that the bands are extremely distinct. The spectral features of clear water are extremely different from that of soil or vegetation. The reflectance is much lower than the other two features for clear water, by the way, and there is no reflectance at all in the near infrared and the beyond near infrared region, if you see clearly. So clear water, so most energy in this case is either absorbed or transmitted. In visible range, that is from zero point 0.4 to zero point 0.7 microns, little reflectance is still observed, which I showed just a few seconds from now. Whereas in NIR range, that is still 1.3 micrometers, it completely absorbs the radiation. So there is no reflectance at all, if you see clearly. So what would you do in this case? It's it actually makes us delineating water bodies from satellite images very easy. You just need to take a near infrared region, near infrared band of an image. Okay, so let us suppose your band is of zero point 0.7 micron to 1.3 micron. You extract an image from a satellite, from any satellite. So you will find that the reflectance is the lowest in this region for water. So whenever you plot the regions, the darkest regions, or the lowest DNs, darkest regions, or lowest digital numbers would be of water pixels. So this is how we actually delineate the water bodies. Delineate water bodies. Let me take an example to explain that. Let us suppose there is a near infrared band image. Okay, and this is an 8-bit image. So if the number of bits is 8, then there would be 2 to the power 8 discretizations of brightness, which is equal to 256 discretizations, or 256 DNs, okay, of that image. So the DNs would vary like this, the digital number, I mean, it would vary from 0 to 255. So totally it would be 256 different distinct DN values. So there would be like 255 different intervals here. Okay, so 256 different intervals here. Okay, so the one lowest would be the darkest, and the one which is the brightest would have the highest DN value. Okay, so we know that in near infrared region the reflectance of water bodies is almost zero. So whereas of the two other prominent features which we discussed here, that is vegetation and soil, they have much larger reflectances in these regions. So you don't need to do anything. You just take, let us suppose you take a filter, you get an image like this. You then take a filter, dn less than equal to, let us say, 15 out of 256. If you put that filter, you would be left with only, and then you set that to 0. Sorry, you set that to 1, and the other DNs, which are whatever DNs are actually greater than 15, you set them to 0. So what will you get? You will get that all the pixels would turn dark which have anything apart from water. So white pixels in this case would be water, and if you try this kind of a mathematical strategy, and the dark or sorry, the black pixels, because we are effectively converting a 8-bit image to a 1-bit image, basically, where there are only two discretizations that of colors, that is fully white and fully black. So fully white would be the one which we are actually assigning as water pixel, and fully black are the ones which are not water. So black pixels would be not water. They may be anything, but that is not a concern for this. So the threshold may be changed. You can change the threshold of dn equal to 15 to, let us say, dn equal to 20 or dn equal to 5 if you are even more strict. And that is how usually we delineate water bodies from images, satellite based images. Now, another very interesting reason why we actually, are so interested in the spectral reflectance or the spectral features. In many cases, we develop some spectral indices why do we develop them? To extract vegetation biophysical properties by vegetation indices. Let us term them as VIs. Okay. So we basically, combine some different spectral bands to come up to some manipulation to come up to know what kind of surface feature that is. So one of the very commonly used vegetation indices is NDVI. NDVI, the full form of it is normalized difference vegetation index. NDVI is the reflectance of the near infrared band minus the red band by near infrared band plus red band. So these are the that is what NDVI is. Now, can you tell me if a pixel, if we are finding the NDVI for a pixel which is of vegetation, healthy green vegetation. So what may be the probable value of NDVI? Will it be positive or will it be negative? NDVI is NIR minus R by NIR plus R. So, looking at this spectral reflectance curve, what can you conclude? Can anyone try? Yes. Do you want? Does anyone want to answer this?
Just a positive value.
Yeah, positive value. So, how large can it be?
Large, sir,
Can
1.2.
there be a range to NDVI? This arithmetical expression of NDVI, can it have any range, or will
Yes,
it be boundless? Will it be from minus infinity to plus infinity?
it's
Minus 1 to plus 1.
Yes, exactly. And for vegetation, as I already discussed, that the reflectance of the near infrared zone band is much larger than that of the red band. Okay, so for vegetation, for healthy green vegetation, usually NDVI would be leaning towards 1, would be ideally from 0.7 to 1. Okay, so that is what it is. So this is primarily a slope based vegetation index metric, slope based vegetation index metric, but it also has some certain drawbacks. NDVI. So nowadays the someone actually is someone trying to ask something? Someone is unmuted. Hello, Mr. Gurumurthy, you want to ask something? Okay, I take it as a no. So NDVI is, although a very popularly used vegetation health or metric, vegetation health parameter or vegetation index, but it also has some sort of drawbacks, caveats. So recent research on vegetation index actually states the drawbacks of NDVI first, and then they try to bring in some new indices. So there are hundreds of such indices, by the way. So I will just briefly mention the drawbacks of NDVI, kind of a NDVI index. So usually the relationship, no, there is a non-linear relationship of NDVI with vegetation properties like LAI. Properties like LAI, and LAI, I think you are hearing it for the first time. So the full form is Leaf Area Index. And LAI is actually projected leaf area by the ground area. It is usually used by the eco-hydrologist, I mean, who deal with the interdisciplinary science of ecology and hydrology to understand how much amount of leaves are there in the vegetation. So, leaf area index, I mean, any idea how much? I mean, okay, so the thing is that let us suppose there is a canopy and it has certain leaves. Okay, you're observing it from the top. So the projection of the area of the leaves at the ground to that of the ground area, that is something known as the leaf area index, and that is a projection of individual leaves, by the way. So due to that, the leaf area index can even exceed one. The usual values, I mean, for forested lands may be in excess of 2 or even in excess of 4. Okay, so it is not between 0 and 1. I mean, okay, so it can exceed 1 in many cases. Okay, so it exhibits some nonlinear relationship with vegetation properties like leaf area index or the above ground biomass. Another very common research, I mean, contemporary research is to estimate the above ground biomass, or which technically is known as the net primary productivity. Uh, it also deals with indices like LAI or NDVI. So, but it shows a nonlinear relationship. So that is one of the drawbacks in this case. Also, NDVI has another major drawback, that it loses sensitivity. It loses sensitivity under moderate to high biomass concentrations. It gets saturated at very high values actually. So that is the second major issue with NDPI. However, I mean, so if we want to advance these vegetation indices based studies, advancements primarily deals with cancelling the soil background effect. Soil background effect. So there is always soil in the background of vegetation, right? So we try to cancel the reflectance which can come to the sensor from the soil, and there are several techniques to do that. One other vegetation index has been devised, which is known as soil adjusted vegetation index, which takes into account soil as its name suggests. I will be explaining about it in towards the end of this session today. And it mostly happens when vegetation cover is sparse. So this is the first variety of vegetation index in which we are finding the slopes in a way. I mean, we are either subtracting or adding two different bands, and then we are indirectly or directly finding the slopes. In NDVI, we did find the slope between NIR minus R and NIR plus R, by the way. So that is the first type of vegetation index. Then there may be some distance based vegetation index also, in which we use some statistical formulations or some Euclidean distance parameters. So that is the second type of vegetation index. Distance based VIs, vegetation index. And finally optimized VIs. Yeah, so they mostly they use the Euclidean distance metric. Euclidean distance is very straightforward, nothing. I mean, if this coordinate is, let us suppose, x1 y1, this coordinate is x2 y2, then the Euclidean distance between the two is termed as, let us suppose it is d, x1 minus x2 by whole square plus y1 minus y2 whole square. I mean, you know that already, it's nothing new, but probably you may not be, I mean, aware of this terminology, so that is why I introduced it. Okay, anyways, so there are a third type of index which is known as optimized vegetation index. So they combine both the first two type of vegetation index, combine concepts of slope based and distance based vegetation indices, vegetation indices. So there are several types of them. But now coming to the actual question, the what would be the moment distance method of moments is used to determine what? I already told the answer to be spectral characteristics, by the way. But I just wanted to give a brief about how method of moments actually, or moment distance relations work in spectral character features. So let's understand that. So moment distance, let us suppose the reflectance is on the x-axis. I am representing it as rho reflectance, and the wavelength is on the y-axis. Let us suppose it is in nanometer, and I mean, let us take any arbitrary reflectance curve. Okay, so one extreme maybe, let us say, 600 nanometer, which is 0.6 micron. The other extreme maybe, let us say, 750 nanometer. So take two ranges in between, lambda 2, lambda 3. This may be the left pivot and this may be the right pivot. Okay, so LP is left pivot. We choose two different pivot points in this procedure, and this is the right pivot. So we basically, in moment distance estimations, we understand, or we formulate the matrix of distance computed from two reference locations, which we are terming as pivots, to each spectral point within the selected range. So the computations are relatively easy. Let us suppose this is the selected range. We take the moment distance about the left pivot as well as the right pivot. So let us suppose the moment distance about the left pivot is, we are effectively doing a integration. So the wavelengths will range from the left pivot to the right pivot in small increments. It is nothing but the hypotenuse. The distances would nothing but the hypotenuse. So we are basically summing up the squares of the base uh, and the perpendicular of the triangles. I minus lambda, okay, rp square, and this is a square root basically. So this would be the first equation, and then we formulate another equation for the right pivot. It ranges from rp to lambda lp, and so again a very similar expression. It's just a Euclidean distance basically between the 2 points, and finally using them we get a moment distance index, which is nothing but MD RP minus moment distance left pivot. And through that, we get to understand the vegetation features. We make a big matrix, by the way, because in general, the hyperspectral remote sensing is the one feature where, is the one case where we use it extensively. And hyperspectral remote sensing, the bands are very narrow. They may be of only around 10 nanometer bandwidth, and there may be around 220 to 230 bands. So you can understand how much of calculation dominant this exercise would be. We finally formulate a matrix for each of the points, and then we get to this MDI. So that is the basic of this procedure. So the first question is over now. The first question effectively means the answer is effectively option B, spectral characteristics. Okay, now let's look at the second question. What is the bandwidth for a sensor having a band in the wavelength of range 0.46 micron to 0.52 micron? Any answer to it? Feel free to unmute yourself and answer if you want. Anything you want to guess or anything? So wavelength range is already given. The range is 0.46 micron to 0.52 micron. What would be the bandwidth? Anything? Any answer? Anything? Any comment or any guess?
Let's see, sir.
C. C is 0.06, and you're correct actually. I mean, the answer is pretty straightforward, right? I mean, the name itself, I mean, is bandwidth, and you just have to take the differences. So bandwidth in this case is the differences between the lower and the upper limit of the range. So bandwidth is 0.52 minus 0.46 microns is equal to 0.6 microns. The answer is C. That is correct. But I also wanted to discuss about the spectral resolution and something known as full width at half maximum. So that is why I took this question. Let's understand it further. So spectral resolution is nothing but the width of each band, in the data set. So we found it already, by the way. There is another concept known as full width at half maximum. It its background actually comes from statistics, but along with the spectral resolution, this value is also reported in general in the uh, in the literature. So it is also reported mostly for hyperspectral remote sensing features in a multi or hyperspectral dataset, and it represents the spread of the band around the center point. Okay, anyways, I mean, I'm taking these terms: hyperspectral, multispectral, panchromatic. You know what these terms actually mean? What is hyperspectral remote sensing? Any idea?
Yes, sir. The
Yeah, please,
hyperspectral
please
has
say.
the band length is more than, and multispectral the band is less, and panchromatic the gray single band, sir.
Panchromatic single band. Multispectral is
100 up to 100 band.
Okay, that is still okay.
And sorry sir, multispectral is 10, you have 20 band,
You're
and
correct. And
and
hyperspectral is?
is 100 band, and fine, and ultra spectral is 1000 bands.
Okay, ultraspectral is, I mean, something which is newly being used. But yeah, hyperspectral, spectral, and panchromatic are the same as you discussed. Panchromatic is a single band image, so it would look just black and white. I mean, it would have some different gray scales. That's it. You cannot make it colorful if you don't. Produce some image manipulations. Okay. Then multispectral has several bands. I will add one more thing to the definition which you gave. The multispectral.
Excuse me, sir.
Sorry.
Sir, one thing I interrupted here, sir.
Yes, please.
Sir, could you provide the demo of the Invis software for the hyperspectral, sir?
Hyperspectral. I don't work with hyperspectral data, by the way. I work on mostly uh, visible. I mean, multispectral data only.
Could you demonstrate the Invis software for the multispectral?
Why do you want to learn about NV? From the next slide onward, I mean, from the next weekly live session onwards, we will take some, coding exercise, by the way. That is my plan from the next class. And, but why are you interested in hyperspectral thing? Rahul? I wanted to know your motivation actually. You are not audible.
Internet connection losses.
Oh, okay. The internet is not working well. Okay, okay. So I will just put the definition first of all. The multispectral may have around 10 to, I mean, multiple bands as the name suggests, but there is also one other thing, that the bands may not be continuous. They may be continuous, they may not be even continuous. That's okay for multispectral, but for hyperspectral remote sensing, the bands need to be continuous always. So that is another restriction to this definition. Okay, so that is the thing. And yeah, I mean, just continuing on what you just discussed, from the next class onwards I will be taking some some practical examples just to make this course a bit more interesting. We'll be doing some coding, or I will be doing some codings, and you see the results and we will interpret it together, the results together. It would be a lot more fun in that way. Okay, the next session would be the next Friday by me. So I'll be doing some MATLAB coding. Okay. And through that, I will try to explain what these results are. Actually, hyperspectral, I am not, I can do that. I have used NV way back in my masters, by the way. But uh, the issue is that nowadays I believe there are not a large number of hyperspectral satellites currently in operation. So I would rather like to explain something which is a lot more contemporary.
Sir,
That is my, interest in the further classes.
sir, yeah, because I'm learning this thing because I have some interview in IIT BHU, sir. That's the reason I learned something in the software, ADA software, QGIS, RGIS, and something learning this topic also, sir.
Okay, okay, okay. Basically these softwares are nothing but codes. The softwares have some predefined codes, and you are running them, and you are finding the results. So we will be rather writing codes from next class. That would be even more fun. You will get to understand the basics of the thing. If you are using a software, the biggest fear I have is that, which I faced as a master student or as a PhD student, was that, whenever I use softwares, I didn't know what went into that, what kind of algorithms went into that.
Yes, sir.
It just happened to be a black box. So I don't want anyone who is studying from me to become like that. So I was also a bit like that. For during my masters, but then I learned. A bit of coding and everything, and believe me, it's very easy to do that. Please don't be daunted by the term coding. It's not that tough. Okay. Anyways, I will proceed with the lecture today. And the full width at half maximum, it is basically the spread around its center point. So that is the definition. So this is also reported usually in the results. Now a thing which I wanted to show you. This is Landsat 8 OLI, operational land imager and thermal infrared sensor. So it has 11 bands. The wavelengths are given on the second column. The resolution is given in the third column. So these are the bands of a Landsat 8 satellite, of Landsat 8 satellite. And Landsat 8 is actually one of the most well used satellite product globally. So one thing which I wanted you to see is that when the wavelengths are getting larger, uh, let us suppose for band 1 the wavelength was 0.43 to 0.45, so the bandwidth was 0.02 micrometers. And as we move into very high wavelengths, let us suppose thermal infrared 1 or thermal infrared 2, the bandwidth is around, what is the bandwidth here? 0.6 micrometers. Bandwidth has increased. The resolution has also increased, by the way. Spatial resolution has also increased. So, do we see that? Do we see a trend that as the wavelengths are increasing, the spatial resolutions are also increasing in general? Can you answer? Can anyone try to answer why does it happen? Why is it happening that an increase in the wavelength is resulting in an increase in the spatial resolution? And please don't compare between a similar wavelength range like from band 1 to band 9. Compare, let us say, band 3 with band 10 or band 11. The wavelengths have significantly changed actually.
So reason behind that, we have to see the more clearance. Like the band gap is very narrow and the resolution is bigger. We have see the clear different distinguish between the all this banded here. The wavelength is distinguished clarity. See that.
Okay, so why not among band 1 and band 2? Because the differences are much lower. It is just from 0.43 to 0.45. This is 0.45 to 0.51. Why not between these two bands? What actually changed between, let us say, band 1 to band 10?
So I
I would
have
give
no.
you a hint. Think from first principles. Go back to the Planck's radiation law. Any idea? Are you getting any hint?
No, sir.
Okay. I will tell you. So one common pattern is that as you move downwards in this table, full screen. Yes, the wavelengths are increasing. So the frequencies should actually decrease, right? Because wavelength and frequency, they are actually inversely proportional to each other, right? This is straightforward. C equal to nu lambda. This is the relation. C is the speed of the light, so C is a constant. So frequency and wavelength are inversely proportional to each other. So as we move downward in the column, the wavelengths are actually increasing. So the frequency should decrease, and if the frequency is decreasing, the energy which can be detected by the sensor is equal to h nu. H is a constant, which is a Planck's constant. Nu is decreasing. The energy will actually also decrease as we move downwards. So in order to detect that energy, that small amount of energy, we would actually require a much larger area. And that is why the resolution is actually also increasing. As we move from, let us say, band 7 to band 11, the resolutions have increased for the same reason. You understood?
Yes, sir.
Yeah. So it is, I think, in technical terms, it is called as the interplay between the spectral resolution and the spatial resolution. You cannot have both of them very high because of this constraint. You need to detect a considerable amount of energy in that band, and that energy can unfortunately not come from a small area because the energies are getting lower as we move into higher wavelengths. So the resolutions also become coarser. So that's the thing.
Sir, in the band of 7, 8, and 9, you explain sir from experience.
8 is panchromatic, so don't include that in the consideration. And you are also, even within this, within, let us suppose you compare between band 2 to band 6, the bandwidths are in general increasing actually. If you observe that, band 5 to band 6, the bandwidths have actually increased. Band 5 bandwidth is just 0.03 microns. This is actually more than 0.03 micron. This is 0.08 micron. So the energies have decreased, but the resolutions have kept same. So in order to detect the same amount of energy, I mean, the same amount of energy can be found out from a 30-meter pixel. By the way, that is the thing. I mean, they get into each bandwidths by finding first of all the energies, and then they devise the bandwidths in general, and they try to make the resolutions as consistent as possible, as they have done in this case. Unfortunately, as we move into very high band wavelengths, the energy diminishes frequently, massively, and hence they have to compromise with the spatial resolution. The spatial resolution, as you can see, has become very coarse as we move towards what do we say, larger wavelength ranges. Correct?
So one thing, sir, like we are comparing 2 and 6. Why not comparing 2 and 3, 3 and 4, 4, 5 and 6?
Even among 2 and 3, you can see zero point 0.6, zero point 0.6. Maybe there is a difference between the third point level, maybe a third decimal after this.
Okay.
It
So
also,
we
of
have,
course, depends on the presence of atmospheric windows. There is
yes, sir.
a, I mean, there is an atmospheric window in the visible range, by the way. Okay, and not everywhere in the infrared range we get atmospheric windows. So absorption and scattering, they may vary with respect to the wavelengths also. Correct?
Yes, sir.
Yeah. So I mean, it's basically a multitude of factors, but the most prominent thing is that I mean, you have to compromise with the spatial resolution if you want a very high spectral resolution, and vice versa. Anyways, now let's move to the next question. What is the temporal resolution of for Landsat 8 satellite?
16 days, sir.
Yeah, it is 16 days. So it revisits one pixel in the land after every 16 days. So this is 16. So I believe I took that. Yeah, that one was also done. This is 16 days. So I mean, let's take an application based on that. You want to prepare a land cover product based on Landsat 8 satellite data. Okay. On, let us suppose, June 1, you get one image over a piece of land. On June 17, you get another image on a piece of land, and both of them may have variety of cloud cover over it. I mean, the cloud cover location may not be same. I mean, because of the cloud cover, you cannot actually detect what's there in the land underneath the cloud. So, any idea how would you mosaic the image? I mean, how would you build a land cover product out of them?
Sir, I have no idea, but I tried, sir. Like
Try,
one
try,
thing,
please.
yes, sir, it's atmospheric correction is something we have to remove the cloud. We have to use the band 9 Mercedes cloud, sir.
That won't work actually. Band 9 works only for the, I mean, primarily is only for the atmospheric scientist, basically. Okay.
Okay, sir.
So actually, this is one issue why, I mean, making a land cover for every temporal scale, temporal time frame is not possible. Okay. So I was recently in a meeting with someone, and that gentleman tried to produce land cover for every year for a region in southern West Bengal, and one of the years data was completely missing. So I asked him what happened, and it was a complete case of high cloud cover in that region. Again, India has four prominent seasonal patterns. We have four seasons, namely monsoon, post monsoon, winter, and summer. So the cloud cover will vary, and also the land cover will vary. I mean, you may cultivate crops only in the Kharif season, and you may keep your you may keep your land free of any cropping during the Rabi season. But if you, I mean, if you take any random date to produce the land cover of that region, that may lead to several sources of error. Okay, so there is a need to definitely move towards seasonal land cover patterns, especially for India. Many places around India, primarily in the peninsular part of India, because they are semi-arid in nature, the farmers don't grow a crop in the Rabi season. The Rabi season is the dry season of cropping. The other reason behind this is that the aquifer patterns are shallower here, and hence they cannot extract as much water as they want out of their need. So that is another reason behind it, by the way. So there is a water limitation. There is, from the surface as well as from the groundwater, which restricts the farming of multiple cropping scenarios in some parts of the peninsular part of India. Whereas in the northern alluvial plains of India, you will see that the farming will happen prominently over at least two cropping seasons, the Rabi and the Kharif season. So where does that water come from? That water mostly comes from the groundwater in the lean period. So that's a storyline basically. Anyways, let's move forward further. How many different gray levels are there in 8-bit quantization? So yeah, anyone wants to answer this?
So 256.
Yeah, how?
So we have studied the scale is 0 to 255, and we have to counting the is 256.
Yeah, you're correct. You're correct. So basically, if there are n bits, that means that there are n quantizations, means n discrete levels. Sorry, 2 to the power n quantizations, or 2 to the power n discrete levels. So if there are 8 bits, that means 2 to the power 8, that is 2 to the 256 discrete levels or quantizations. So this will look like this. If you change it into the dn scale, the lowest dn or the darkest dn would be dn equal to 0, and the brightest dn would be dn equal to 255, not 256, because we want 256 quantizations, 256 distinct numbers. So 0 is also considered as a number. So the brightest one, or the one which is fully white, will look as 255. Will be read as dn equal to 255. Anyways, now I also wanted to give you a brief about the data types through which we store these quantizations on computers. So first data type may be signed 8-bit integer, or it is actually written as signed int 8 in data type format. So in this, if there is a 8-bit thing, then there are 256 quantizations, but it is signed, so it will contain negative values also. So they store values from minus 128 to 127. So if you observe, the total number of numbers are nothing but 256 itself in this case. But they're writing, it is a signed way of writing the data type, the same data. Then there is unsigned int 8. From the next session, we will be doing some coding kind of an exercise, so you will understand it much better, by the way. So this will be 0 to 255. Then there will be signed int 16, means it is a 16-bit product. So it will range from minus 32768 to 32767, and the fourth one may be unsigned int 16, which will be 0 to 65535. So that's the variability basically. So you can change the number of bits. You can have an 11-bit product also, by the way. So nothing. Only the numbers would change.
So one thing I ask, sir.
Yes.
What is signed, sir, and what is unsigned?
Signed means it also has negative. It stores data in the form of negative values also.
Okay, sir.
So signed versus unsigned, you see that the total number of values are 256 in both the cases, by the way. But the storage type, the storage of the data in the computer in signed int 8 pattern is also in a negative way. So they actually try to keep the data symmetrical actually about zero. That is the funda. In signed kind of data type, they try to keep the data symmetrical about zero, and that is why they have negative values also. Understood?
Yes, sir.
Oh, thanks. Let's move further to some other questions. In the visible region, the spectral reflectance curve of vegetation is dependent mainly on A. Leaf pigment absorption, B. The internal structure of the leaf, C. Leaf water content, or D. Leaf area. So I already discussed it. It depends on leaf pigment absorption, and that is why I actually explained it in details earlier. It's all written also. So I will be uploading these illustrations by the end of the night, so you can read it later. And that pigment we all know is chlorophyll, which is responsible for something called as photosynthesis. The next question is, the transmittance of vegetation is maximum in which of these bands? I discussed this question also. The transmittance is actually the greatest in the near infrared band. So this is also done. Then select all the correct statements regarding a plant subjected to water stress. Okay. A. The large chlorophyll absorption in blue and red bands. B. Less chlorophyll absorption in the blue and red bands. C. Increase in red reflectance. D. Decrease in the red reflectance. Okay. So, plants are related to water stress. So, if there is a stress vegetation, then I already discussed that there would be an increase in the red reflectance, and there would be less chlorophyll absorption in the blue and red bands. I already discussed these things in details a bit earlier. And finally, the sudden rise in the reflectance between the red to NIR regions is known as A. Green edge, B. Red edge, C. Blue edge, or D. NIR edge. It is known as red edge. It's just a terminology, so nothing to explain there. But I will give a bit more detail about it in due course of time. But anyways, let's come back to the reflectance curve of vegetations. Yeah, so this is how the vegetation reflectance curve look like. You see that there is a huge slope. As we transition from visible range to the near infrared range, it suddenly increases. The spectral reflectance curve suddenly increases within a very small deviation of the wavelength. So this is something known as the red edge actually. I will also write the definition. Red edge is the rapid change of reflectance of vegetation in the NIR band of electromagnetic spectrum. Now, chlorophyll, we know that it absorbs light, absorbs energy mostly in visible range, and it becomes almost transparent at a wavelength range greater than 0.7 micron. The cellular structure of the vegetation that causes this infrared light greater than zero point 0.7 micron is nothing but infrared. So to be reflected because each cell acts like an elementary corner reflector at that wavelength range. So the change in the reflectance can be 5 to 50 percentage from 680 nanometer to 730 nanometer. Okay, so and it helps the plants in avoiding overheating during photosynthesis. Photosynthesis is actually, biologically speaking, a highly energy heat expensive uh, process, and this what do we say? This elementary corner reflector kind of a mechanism actually leads to uh, lowering of the heat, and also that is the reason why the reflectance changes so much in this region. So it changes the reflectance from 5 to 50 percentage as we move from 0.68 micrometer to 0.73 micrometer. So it's changing massively. So this may be around 5 percentage at this level, and suddenly it crosses around 60 percentage, and that happens because of this reflector property of the chlorophyll, and also as a biological strategy to avoid the overheating because of photosynthesis. The primary task of chlorophyll pigment is basically to photosynthesize or assimilate the atmospheric carbon into biomass. That is what they do in the day. So we are done for the questions which I wanted to discuss for the day. But I also wanted to discuss about one other thing. Red age. Keep. Okay, it got omitted probably. I have to write it again.
Excuse me, sir.
Yeah, sorry.
Sir, in a plant have a stress condition.
Yes.
Uh, the reason behind we have to see a plant has a stress, so we have used the radiage.
Can we?
When a plant has in a stress condition, not in a very good condition and not a very healthy condition, we see that the plant has a very stress condition. We use to the reason is radiage reason, sir. I ask questions,
No,
sir.
red edge is basically the thing that I mean the mechanism that the reflectance changes massively. I mean, as we move from the red band to the near infrared band, right? I mean, the reflectance curve for a vegetation looks like this. Suddenly, it peaks after the red band, and it explains why it happens. So there is a mechanism behind it, and that is what I was discussing. And it is also a strategy by the plants to avoid the overheating. There is some certain amount of heating already which happens during the process of photosynthesis. So in order to avoid overheating, there the cells act like mirrors. So whatever comes to them, they reflect them back, and that is why the reflectance also increases suddenly within that range. Okay, Rahul.
Yes, yes, sir. Yes, sir.
Yeah. Vegetation in the near infrared range of electromagnetic spectrum chlorophyll chlorophyll absorbs mainly in visible range, and it becomes almost transparent at lambda greater than 700 nanometer, which is zero point 0.7 microns. So this happens because of the cellular structure. The cellular structure of vegetation that causes this infrared light to be reflected, because each cell acts like an elementary corner reflector. So this is a strategy to avoid overheating during photosynthesis. Uh, yeah, keep next slide. To avoid overheating during photosynthesis. So due to this, the change in reflectance is actually huge. Can be 5 to 50 percentage from 680 nanometer to 730 nanometer. So it actually helps the plants to avoid overheating. I mean, that's a strategy. I mean, they don't want to absorb anymore. I mean, how do you think a body's heat would increase? How would you think that a body's temperature will increase? It will increase if it absorbs a lot of energy, right? What if it is not doing that? If it's acting like a mirror, let us say, so whatever energy which is incident on it, it will be reflected back again to where it came from, resulting in the absorbance to decrease but the reflectance to increase massively. And that is why the reflectance increases a lot within this very narrow band of wavelength. So that is a scientific reason behind this, by the way. Before going into the last part of today's discussion, I wanted to discuss also about another vegetation index. Two prominent vegetation index, by the way. We already discussed about the normalized difference vegetation index, NDVI. I also want to discuss about the soil adjusted vegetation index, SAVI, and the leaf area index, LAI. And LAI in general is used extensively for modeling of evapotranspiration over the different regions. So it becomes extremely necessary. I will be taking another slide to discuss that. Soil adjusted vegetation index. So we discussed that NDVI faces a drawback that whenever the vegetation content is low, so the background reflectance from the soil would actually result in erroneous results in the NDVI, because soil and plants, they have very similar reflectance patterns actually. Okay, I mean, in terms of magnitude, I mean. Okay, so whenever there is a sparse vegetation condition, NDVI may not perform very well. So in order to counter that, another vegetation index has been defined, which is known as soil adjusted vegetation index, or SAVI. So it is used to minimize soil brightness influences, in very simple terms, reflectance, using a soil brightness correction factor. And it is used mainly in arid regions. Why arid? Because there is sparseness of vegetation. in these regions. Okay, so SAVI, the formula is like this: NIR minus R by NIR plus R plus L times 1 plus L. So you know what is NIR? The reflectance in the near infrared band. R is the reflectance in the R band, red band. L is something which you don't know, by the way. So L is a function of the amount of green vegetation in that pixel. It will be 1 if there is no green vegetation, and it will be 0 if there is very high green vegetation. And in between values for different vegetation fractional cover, by the way. So when L is 0, SAVI becomes nothing but NDVI. SAVI becomes nothing but NDVI. And that should be the case also, because NDVI was defined for such scenarios only. So uh, we are done with the SAVI discussion. Let's discuss a bit more about the LAI, leaf area index, another
So what
very
is L,
important
sir?
uh, vegetation index.
Excuse me, sir.
Yeah, please ask.
Sir, what is L, sir? L plus something you can say.
L is a function of amount of green vegetation in that case. So it would be 1. I mean, by definition, in this formula, it would be 1 if there is exactly no green vegetation, and it would be 0 if there is very high green vegetation in that pixel.
It's written as 1 plus L, no, sir?
Yeah,
It's written here formula 1 plus L.
yeah, in the numerator, yes.
Okay, sir.
And a bit about LAI, another very common vegetation index. We will be, from next class onwards, we'll be doing our exercises on these indices using some coding purpose. I don't want you to, I mean you can use softwares and everything, but I want to explain the basics first. Otherwise there is no joy of getting results without knowing how it how they actually how you actually got to the results. So I believe firstly knowing how you came up with the results would be more interesting. So we will do that from next live session onward, by the way. So leaf area index, we are depicting it as LAI. It can be found out by statistical methods or physical methods. So LAI, the definition I already gave was the projected leaf area by the ground area. So LAI can actually be even more than 1. So you should not be stunned if you see the value of LAI to be more than 1 anywhere. Okay. So the statistical methods are the one in which they actually link link up some surface reflectance or vegetation index with the LAI using some empirical relationship. Empirical statistical relationships are always data driven. So that is the case with it. Between surface reflectance or vegetation indices and physical methods, they are based on radiative light transfer processes. I mean, whatever amount of light which falls on the canopy, out of them, how much would be intercepted, how much would be transmitted, and everything. It's a very complex thing. The physical method is a very complex way to find out LAI, by the way. Transfer processes within the canopy. Okay, so how do we find out the LAI, by the way? I mean, or season. I mean, with respect to the different seasons. Let's check it then. So we use something known as the Beer-Lambert law. I mean, those of you who might have done experiments in the environmental engineering lab on spectroradiometers, they might be already aware of it, or spectrometers, they might be already aware of it. Yes. Anyone asking something?
No, something know the beer limit. Let's say.
Okay, everyone is muted. So it comes from Beer-Lambert law, by the way, and the funda is to understand what fraction of visible light transmitted through the canopy to the ground, which is something also known as the through the Beer-Lambert's law. Okay, so the equation is I 1 minus qt by q naught 1 minus e to the power minus k times LAI. So K, first of all, K, this coefficient K is something known as the extinction coefficient, very similar to the one which I used with aerosols in the last weekly live session. Extinction coefficient, and it usually ranges between 0.3 to 0.6, and it physically means the amount fraction of visible radiation intercepted by unit area of leaves. I here I this I here is a fraction of light intercepted by increasing layers of leaves. Then Q naught is the visible radiation on the cloudless days incident over the canopy, and QT is basically visible radiation transmitted through the accumulated layers of leaf. So that is its logic basically. And this LAI you will study. I mean, if you happen to take a course on advanced hydrology or eco hydrology sometime later in your life, you will understand that it is very important. It is used to estimate the biomass. It is also used to estimate the evapotranspiration in many cases. So it's a very essential quantity to understand. So today we are almost done, but before leaving, I would want to discuss about some of the very prominent satellite sensors. So some of the landmark satellites, I mean, the ones which I found very interesting are the ones I wanted to discuss with you guys. So one of them is the NOAA AVHRR. The AVHRR means Advanced Very High Radiometric Resolution Satellite. The radiometric resolution was 11-bit in it. So there would be 2048 discretizations or the grayscale in it. The temporal resolution is also very decent. It's around 103 minutes, and uh, it has a relatively coarse spatial resolution of 1.1 kilometer. So that was the first satellite. Then Landsat 8. Landsat series is actually one of the most well studied satellite product worldwide. It is over 50 years old now. I think it started around sometime in the 1970s. So you can even, I mean, freely download the Landsat pixel data from your own village, let us say, village or city, and you can understand how much of the land cover transformation has happened in that region. So Landsat satellite is a remarkable satellite in that sense, and this is the one. I mean, this discussion. I mean, I wanted to discuss about Landsat 8, by the way, which is the latest in this series. I think Landsat 9 has also been launched, but I'm not well aware of it. Anyways, so it was Landsat 8 was launched in 2013, and I already discussed the spectral resolution. The spatial resolution is 30 meters, very, very, very fine. The radiometric resolution is 12 bits and 16 bits when they process level 1 data products. Temporal resolution is 16 days. We discussed it in one question already. Then Iconos I took because it had a very fine spatial resolution. The spatial resolution is barely 0.82 meter in its panchromatic band and 3.28 meter in the multispectral band taken at Nadir. And 1 meter at again panchromatic 4 meters multispectral resolution in some off nadir position. So this was one of the finest spatial resolution product I could find. There is another one currently which is being used extensively, which is known as Sentinel. Sentinel satellite is also quite fine spatial resolution product, by the way. Then Cartosat is the one which was launched by ISRO in 2007, and it was for cartographic details, as the name already suggested. The spatial resolution is very fine, 0.81 meter only, and the spectral resolution, it's only a panchromatic band, by the way, and the radiometric resolution was 10 bits. Then Spot 6, another very interesting one. The spatial resolution is just 2 meters, and it depends. I mean, with respect to the bands, by the way, radiometric resolution of 12 bits and the temporal resolution of around within 26 days they can actually revisit any place. So that's the specialty. Then QuickBird was launched in 2001 and very fine spatial resolution of 0.61 meter for panchromatic band and 2.4 meter for the multispectral bands. 11 bits again, and temporal resolution varies with respect to the area and the angle of image collection. Then this one, the Earth observing one, or something which we also call as Hyperion. It is a hyperspectral kind of a satellite sensor. It had 220 unique spectral channels, and they were 10 nanometer of spectral bandwidth each. And through that, I mean, the use of that was that, I mean, through this you could find out the spectral features of vegetation or any other surface feature much more easily. Then resource sat. Uh, Again, several bands, and several bands have different spectral resolution, different radiometric resolutions, and the spatial resolution for list 3 was 23.5 meter, and avix another sensor was 56 meter at Nadir, again the one by India itself. Then radarsat is a Canadian one, and it was used for disaster management, monitoring of ecosystems, and maritime surveillance. Resolution varied from 3 to 100 meters, and it was a microwave remote sensing sensor. This course would probably emphasize on optical and thermal infrared or near infrared images only. Uh, it won't cover in detail the microwave remote sensing, by the way. So anyway, so this would be probably the last such discussion about microwave satellite product in this entire uh, course of weekly live session. Then OrView, I mean, so I've listed a few. So OrView was another one, which was launched way back in 1997, and very coarse spatial resolution of 1.1 kilometer at the Nadir. Swath was very wide of 2800 kilometers. Radiometric resolution 10 bits. The revisit time was 1 day, which was decent. So here they are. Another last thing I wanted to discuss with you is that the impact of spectral resolution on how you interpret the reflectance of the images. Let's check it out. So let us suppose we have only two bands versus four bands in an image. A two band image, let us suppose this is band 1, B1, this is B2, versus let us say a four band image in the same range. This is lambda 1, this is lambda 2. Again, we are between lambda 1 and lambda 2 only, but we will have four bands 1, 2. So this is B1, B2, B3, B4. So what do you think? I mean, let us suppose this is configuration number 1, this is configuration number 2. So out of these two configurations, out of which configuration will you be able to see the, I mean, understand the spectral features better? Any answer?
Sir, two, sir.
Yeah, 2. Why?
We have bands, sir. Like like the blue color, we have to know about the light blue, dark blue, and we know all the details of the real life vegetation also, sir.
Yeah. So the actual spectral feature may be something like this. So this will try to show it like this probably, but this will show it just like this. So you will of course be able to understand more from the configuration number 2, right? So in hyperspectral sensors, the channel widths, the bandwidths are so narrow that you actually get to know about the spectral features much better. And scientists have actually even developed several spectral libraries. They have already conducted experiments in lab using spectroradiometers, and they have already created spectral libraries. I mean, how let us say soil would look at say 5% of moisture content, soil with 10% moisture content, so on and so forth. Water stressed at 5%, stressed at 10%, and so on and so forth. Or soil mixed with iron, I mean, this much amount of iron versus that much amount of iron. So they have created spectral libraries already, and then they have some spectral matching features also. I mean, you may extract a pixel out of your hyperspectral remote sensing exercise, and then you go into that spectral library, which is completely digitized, and then it will tell you that in that pixel how much amount is, let us say, vegetation, of what type of vegetation, how much amount is soil, what kind of moisture content does the soil have, and so on and so forth. So it will give you a lot of details. So that's the funda behind, I mean, why we, want to learn about the hyperspectral remote sensing also. So we are done for the day, but if there is anything to ask, please feel free to ask me.
The last thing you have to say about the spectral library. So we have to where we see in Python, you have in another areas.
Sorry, I couldn't listen to the last question you asked me.
Many scientists have to collaborate and make a library in their lab. So we have to see where these libraries are. In Python, you have in browsing forms.
That I'm not sure about because I don't. I mean, as a researcher, my interest is not in hyperspectral remote sensing. I work on ecosystems, basically terrestrial ecosystems, and I'm doing my work based on optical and infrared remote sensing wavelengths. So I'm not sure about that. I'm not the best person to speak of that. But yeah, they have libraries in NV also. Rahul, they have libraries in NV also, by the way.
Okay, sir.
I used it way back during my masters, so we learned that at that time. But I currently don't have a subscription for NV, so I cannot show that to you. And
Sir,
I don't use NV at all.
I am also a
Yeah, yeah,
master
yeah.
student from environment science. Not a very code but technical department. I'm basically environment science, and I am learning this DPG